Welcome to Space News from the Electric Universe, brought to you by the Thunderbolts Project at thunderbolts.info. In the recent Space News episode, Electric Universe Geology, A New Beginning, Thunderbolts contributor Andrew Hall began laying the foundations for revolutionary concepts in Earth geology. Hall introduced his hypothesis based on the principles of plasma physics and electrical engineering for the formation of mountains and other landforms and features. In part 2 of his presentation, Hall continues his discussion of evidence that massive electrical discharges in Earth's atmosphere have profoundly shaped our planet's surface.
In the first part of A New Beginning, we looked at triangular buttresses that form on mountains and within the rims of craters. We looked at evidence they are layered in place and molded in form because they were created by supersonic winds and sonic shock waves. We discussed shock wave properties and how they form standing reflected waves that channel the winds and imprint the landscape with the exact shape of the waveform. Now I'm going to show you some more mind-blowing evidence. Our first topic in part 2 is harmonics. The images shown are color-enhanced Schlieren photographs of reflected shock waves in a wind tunnel. Schlieren photography basically captures the refraction of light by the shock wave because a thin sheet of the shock wave is at a different density than the surroundings. While looking at these images, remember that the shock waves are three-dimensional, and these Schlieren photos see the wave edge on. Wind tunnels typically show supersonic flow between two surfaces. The initial shock reflects from the walls of the tunnel, creating two triangular waveforms adjacent to each other. The diamond patterns that form between the triangles are often called shock diamonds. In the case where a supersonic wave is created in the air, it is unbounded above, so the only surface reflecting it is the ground, and it creates a row of triangles instead of the diamonds. Looking at the photo, the initial wind speed in the first frame on the top left is Mach 2. It shows the shock wave producing 1.5 triangles, or diamonds. The wind tunnel is charged with gas in a pressure vessel, so the gas flow progresses, the pressure and mass flow decrease, lowering the Mach speed of the wind. The subsequent frames show instability in the shock waves as the winds slow. The waveforms compress and the angles of the primary and reflected waves grow less acute. Vertical shock waves form, called normal shocks. Normal shocks are standing waves too, but instability causes them to migrate. They travel through the triangles, distorting their shape where the normal wave interferes with the reflected wave, and it causes more reflections. New smaller triangles form and replace the original standing wave. This is harmonic reflection of the primary shock wave that occurs over time as the energy of the event dissipates and transient effects take place. In the final frame, on the bottom right, the wind speed has slowed, the triangular waveforms are smaller and higher frequency. There are 7 shock diamonds where there were initially 1.5. This sequence of harmonic reflection is evident on the triangular buttresses stacked on the sides of mountains. As seen in the images to follow, triangles are stacked upon triangles in harmonic multiples as the successive layers of material were deposited by supersonic winds, tunneled by the reflected shock waves. The first image in this group is most instructive. In it, the lowermost layers of a harmonic waveform can be seen to have begun to form at the outer edge of the preceding layer. Do you see the small waveforms and the serrated edges of the preceding waveform the arrow points to? Those serrations show the distortion of waves just before they snapped into a new harmonic configuration. This image demonstrates how the scale of the harmonic can change dramatically, showing the waveform suddenly shatter into multiple reflections. First, there is the large waveform that fills the frame. It's already breaking up from an instability, a normal shock that slices down from the triangle's apex. Then 7 harmonic waveforms fill the wavelength. Actually, there are more, but they extend out of the picture frame. Then these break down to 2, 3, or more waveforms each. I've circled a set of 7 little baby ones that appear within the wavelength of their parent. This image has mineral layers that also highlight the harmonics. Here's another shot of the same mountain. These are undeniably harmonic wave reflections from a shock event. Here's one more image of this same mountain. It's one of my favorites. Note the small row of harmonic waveforms high on the mountain in the center of the frame. Also note the large vertical crack, or fault line to use a conventional term, that appears on the right of the small waveforms. That was caused by a normal wave that apparently followed the formation of the triangular buttresses because it sliced right through them. There's a second normal shock to the left of the small waveforms that is perfectly parallel to the one on the right. It has been partly eroded by water, but you can see the crack at the bottom and the top. Then there is a third, farther to the left, that is hardly discernible, but it's there. They are almost evenly spaced and perfectly parallel to each other. Harmonics are evident all over the place on this mountain. You can see here how the buttresses build ridges as they layer outward. The waveform breaks down into harmonics, and these continue building smaller ridges. Some narrow and cancel, some widen. They jostle each other, competing for space and the energy of the inflow winds. But the inflow winds continue to build the buttresses facing outward, perpendicular to the wind flow. It has an almost organic nature, like cellular automata replicating. In fact, I think it is how these can be simulated, using a mathematical algorithm of cellular automata. The energy dissipates the shock envelope, but continues building ridges for a long distance at a lower energy. The howl of the winds must have been beyond imagination when this happened, each waveform producing a different tone but in harmonic resonance. It must have been like a symphony of giant trumpets. Transients in wind speed, Mach angle, and multiple reflections create instabilities in the waveforms. Unstable waves segregate and fan away from each other under expansion, fragmenting the waveforms. Or they bunch together in compression, pressing waves against each other. Shock waves don't like to cross, but fold against each other. As wave fronts compress, the waveform can be squeezed and canceled out. This image, 3 waveforms compress, distorting into curves where the waves, pressed against each other, bend the center waveform almost circular. In the following layers, the pinched wave is canceled altogether, and the surrounding waveforms have joined, stretching wavelengths to close the gap. A similar wave cancellation has occurred in this image. Here, the center ridgeline is canceled by neighboring waveforms, and they've expanded to fill the wavelength. A diagonal shock line appears, cutting the mountain where the cancellation occurs. It crosses in a stepwise fashion, a few layers at a time, causing it to zigzag. This shows the temporal relation of its movement to the triangular waveform layers. Note the ruler-straight shock lines that divide the adjacent triangular buttresses. Complexity is found within the shock fronts, inside the triangles themselves, as pressure and density variations. Here is a wobbly, unstable waveform. Note the density variations form a circular feature near the top of this Schlieren image. Now look at the same feature on this distorted triangular buttress found in northern Arizona. Also note how the edges of the triangle draw in towards this circle, just as the waves near the top in the Schlieren image do. The 3 small buttresses below the hole show a strikingly similarity to the size and location of those in the same position in the Schlieren image. Here's another hole created in a triangular buttress. This one is in Iran, and here's another one that was formed in Utah. One type of wave expansion is called a Prandtl-Meyer expansion fan. It occurs if the shock trajectory is forced to change abruptly. The next several images show such an expansion fan. The region sits near the Persian Gulf, alongside the outside curve of a mountain arc formed by basin and range mountains. The fan forms where the arc current apparently turns sharply, curling almost 180 degrees in its trajectory. The fan features are about 10 kilometers long. The triangular buttresses are extremely well defined, and the area is surrounded by ablated material. Harmonics are evident where the primary shock passed, as well as on the pressure ridges that define the expansion waves. Buttress layering is obvious and shows the direction of the winds at 90 degrees to the pressure ridges, and the reverse slopes also show the layering clearly. And each successive ridge in the fan is smaller and shows fewer layers than the preceding ridge, as the preceding ridge grew to block the winds coming from the left in this image. The expansion fan makes clean, straight pressure ridges, expanding away from the blast zone. It's obvious the entire structure is the result of a single coherent event. And here's a final view of the fan from the opposite direction. Iran, by the way, has this region of mountain arcs where these features are particularly evident. The land is arid and has little vegetation, so you can see the bones of the mountain. But these features are found all over the world. This road cut in Iran is sometimes described as a slip fault that created the Horse Graben, or basin and range region, where this is found. That isn't the case, of course. The slice in the ground was left by the primary or incident shock on the left side of the V, and its reflected shock on the right side of the V. This is the boundary region where the initial shock meets and reflects from the ground. The incident shock curves sharply downward and the reflected shock is nearly straight. Where the reflected shock and incident shock meet, there is a feature called the lambda foot. Note the incident shock curvature and the particular dip of the sedimentary layers within the V. They are similar to the angled transmitted shock shown in the V of the diagram. Here's another image of the road cut with a broader view. In this view, the lambda foot at the bottom of the V is easier to discern. Also, a feature not even originally shown on the diagram, the cut in the center top of the V that results from a shock that curves downward, normal to the expanding corner of the reflected shock, and I've annotated that in red on the diagram. This shock feature is along the side of a hill that can be seen stacking in layers to the left. It should define the outer boundary of the initial shock wave. If so, it should form a ring around the mountain, and a similar V-shaped cut should be found on the opposite side of the hill. If true, the incident angles and distance between this V and the predicted V on the opposite side hold information about the height of the apex of the passing wave. Now, are you beginning to believe your lying eyes yet? Let's recap what we have seen so far. In part 1, we saw triangular waveforms exhibit compression and expansion from superimposed longitudinal and transverse waves. In part 2, we've seen that triangular waveforms exhibit harmonic repetition consistent with reflected shock waves. They exhibit superpositioning and cancellation under compression, consistent with reflected shock waves. They exhibit normal shocks, expansion fans, and features of density variation, consistent with reflected shock waves. And boundary layer features of reflected waves can be found in the substrate of the blast zone, as seen in the road cut in Iran. Let me emphasize this. These are undeniably supersonic waveforms. If anyone has an explanation for harmonic waveforms to appear on mountains by any other means than what I'm describing, whether a mainstream theory or otherwise, please clue us in. But I'm not going to hold my breath. These features can't be readily seen without aerial or satellite views because they are too large to see from the ground. Geologists should put their pickaxes, seismographs, and Latin dictionaries away and get a free copy of Google Earth. Actually, I know and I've worked with many geologists, and I respect their knowledge. Earthquakes, meteors, volcanoes, and erosion still form the landscape. But the underlying physics is misunderstood. The gravity-only, billiard ball bouncing particle theorists have infected all of science with their zombie virus. It's time for enlightenment, for mankind to finally understand the universe, how it's governed by fields, not particles, and that Earth is electric too. And so are you. So turn up the gain on your antenna and stay tuned. In part 3, we'll take a look at some electrical effects in larger mountain structures. Thank you for watching and for all of your kind comments.
For continuous updates on space news from the electric universe, stay tuned to thunderbolts.info.